A few months ago, I was browsing through some of Veritasium's old videos when I found this: the big misconception about electricity. And of course, I didn't want to be harboring any misconceptions about electricity, so I hurriedly clicked on the video to update my understanding. And may I say, my understanding was updated. You see, I used to think that energy flowed through the wires in a circuit, but it turns out that it actually flows around wires, as shown by the Poynting vector. And because of this fact, a light bulb placed right next to a switch will turn on almost instantaneously when the switch is closed, regardless of the length of wire that connects the two components. And to think, I used to tutor people in this subject. I've never been so ashamed. But wait a minute. Doesn't signal latency depend on cable length? And if energy flows through the middle of a circuit, does that mean you can alter the energy flow by adding objects to the middle of the circuit? And when the video ended without answering some of these questions, I realized I was going to have to find the answers myself. Combing through the most authoritative sources that I could find, I slowly gathered various pieces of the puzzle. And when I've had the full answers in front of me, I came to the realization that Derek really didn't do a very good job explaining some of this stuff. So, for the 7 people out there who are still interested in this question and are looking for more insight, this is the video for you. Derek's main point is that energy does not flow through wires, but instead flows through electric and magnetic fields, which raises the question, what is a field? To properly appreciate fields, we first need to go back to a time before they existed. Back then, in the good old days, if you wanted to move something, you had to push it with your hands. And if you weren't strong enough to push it, you got an animal to pull it. Movement required physical pushing or pulling. And with that understanding, there was harmony in the land. Unfortunately, soon after, a great mystery arose and threatened to overturn that understanding. I'm speaking, of course, of magnets. Magnets, you see, can push or pull on each other without having to physically interact, flying completely in the face of everything that we knew and loved. Seeing their great understanding challenged, mankind took the only reasonable approach. They declared magnets to be the work of sorcery. And with that issue settled, they were free to move on with their lives. But unfortunately for them, it didn't take long for some people to realize that other materials, such as amber or wool, also had the ability to repel nearby objects. And then Newton came along and really screwed things up when he discovered that planets also pull on each other, but this time across massive distances. At this point, people realized that, unless they were going to let the sorcerers win, they'd have to come up with a different explanation. And the explanation they settled on was field theory. Imagine that you lit a fire inside an enclosed room, and before you passed out from the smoke and carbon monoxide, you'd feel the room get warmer. But how can this be? You aren't standing in the fire. The fire isn't even touching you. So how could it be making you warmer? The answer is that the fire heats up the air immediately next to it. This small pocket of air warms up a larger pocket of air around it, and in this way the pocket of warm air grows until it eventually reaches you, warming you up. So the fire passes heat to the air, and the air passes heat to you. You might call this a heat field. This same idea is used to explain electric, magnetic, and gravitational forces. When two charged particles get close to each other, they don't directly interact. Instead, each particle creates its own disturbance in the surrounding electric field, and it is this disturbance in the field which acts on and repels the other particle. And because objects are only being acted upon by the nearby field, there is no more action at a distance, preserving the theory that objects only interact with things immediately next to them. One other thing to know about fields is that they do not update instantaneously. We have again our 2 electrically charged particles. And let's imagine that one of the particles were to suddenly disappear. In such a scenario, the second particle would still, momentarily, feel a force on it. Changes in the electric field travel through space at a finite speed, and so the force on the second particle will only disappear once the local field updates to reflect the missing first particle. Updates to the field move at a speed of 300 million meters per second, and this speed is often referred to as c, or as the speed of light. Once scientists agreed upon the existence of fields, they next needed a way to draw them. They eventually settled on the following convention. Let's say there is a positively charged particle. To draw the electric field around it, imagine that this particle is surrounded by more positively charged particles. We then draw the repulsion force that each particle would feel. If you then remove the surrounding particles, you are left with a ring of outwardly pointing arrows, which is how we represent the electric field. If we wanted to draw the electric field around a negative particle, we use the same procedure. And since positive particles are attracted to negative particles, the arrows that we draw all face inwards. These sets of arrows, which show the force on any nearby positively charged particle, form our basic building blocks of drawing electric fields. Note that since positive particles are used to generate the arrows, a negative particle will be pushed in the opposite direction of that shown by the electric field. Now let's say we want to represent the electric field created by multiple particles. Performing the same procedure as before, we see that the test particle experiences a pair of forces, and if we add these two forces together, we get a net force to the right. Performing this exercise at every possible location gives us the overall electric field. We could instead analyze a pair of positive particles. With this setup, we see that in most locations, the two forces acting on the test particle add together, resulting in a stronger force. However, in the middle of the field, the forces on the test particle cancel out, resulting in zero net force. So, when two positive particles are brought together, the electric field around the particles grows stronger, which is shown by an increase in the number of arrows. Meanwhile, the field between the particles gets weaker, which is represented by a lack of arrows. Now at this point, I bet a lot of you are thinking something like, so big whoop, so field theory solves the force at a distance problem. Is there anything else it's good for? Well, I'm glad you asked. Imagine that these two magnets are a pair of charged particles which are pushing against each other. As I bring the left particle towards the center, I have to overcome the repulsive force, and am therefore adding potential energy to the particle. When I release the particle, it converts that potential energy into kinetic energy. Now, what if I tried that experiment again, but this time I released the right particle? As you may guess, it also flies away, onto the floor, and probably down an air vent. But how is that possible? I put potential energy into the left particle, and yet the right particle was the one to gain the kinetic energy. Was the energy somehow transferred between the two particles? Did the right particle steal the energy from the left one? To answer this question, we'll run the same experiment, but with some marbles and a spring instead of magnets. And with this setup, we see that the potential energy is being stored in the spring, not in the marbles. And when I let go of either marble, the spring is transferring its potential energy into the marble as kinetic energy. In a similar fashion, when I bring the two particles together, the electric field that they generate acts like an invisible spring, storing potential energy. The stronger that the field gets, the more energy that is stored. And when I release either particle, the field transfers the potential energy into the particle as kinetic energy. Therefore, field theory solves not only the force at a distance problem, but also the energy transfer problem. Now, my big brain viewers have probably guessed where this is going, but before jumping into the jackpot, let's dig into this energy storage concept a little deeper. Let us again pretend that these magnets are all positively charged particles, and that this particle has a charge of 1 coulomb. When we release the particle, it flies off with some amount of kinetic energy, let's say 2 joules worth. Let's try the same thing, but this time we double the number of particles in our stack, meaning it has 2 coulombs of charge. Now when it flies off, it leaves with 4 joules of kinetic energy. And when we try the experiment with a 3 coulomb particle, it flies off with 6 joules of energy. Through these experiments, we have discovered a property of the electric field created by these stationary particles. Any charged object released from this location will gain an amount of kinetic energy equal to twice the object's electric charge. Phrased another way, at this location, the electric field has an electric potential, or a voltage, of 2 volts. And since it is usually more important to know the amount of energy that can be extracted from an electric field, as opposed to knowing the strength of the electric field itself, electric potential is the quantity we are usually interested in when working with electrical systems. Electric potential can also be used to calculate changes in kinetic energy when moving between different fields. For example, let's say that a 2 coulomb particle starts in an area with a potential of 5 volts and then moves to a location where the potential is 2 volts. To find the change in the particle's kinetic energy, you take the difference between the starting voltage and the final voltage and then multiply that by the particle's charge. In our example, we see that the particle has gained 6 joules of kinetic energy during its move. This equation can also be used when dealing with negative voltages, such as when moving to a region with a potential of negative 3 volts. In this case, the particle will gain 16 joules of kinetic energy. Negatively charged particles work just as well with this equation. If you have an electron that flies away from a region where the potential is negative 8 volts, then by plugging in the charge carried by a single electron, you can find that it will have picked up 12 times 10 to the negative 19 joules of kinetic energy. Though, since using exponents is for suckers, when engineers are late for the bar on a Friday night, they just call that 8 electron volts of kinetic energy and wrap it up early for the week. Now that you understand voltage, we can explain what happens to a wire when it is hooked up to a power source. When I touch this wire to the negative side of a 5-volt battery, the surface of the wire will gain an electric potential of negative 5 volts. And since we have learned that electric potential is the result of electric fields, that must mean that excess electrons are flowing into the wire, giving it a negative electric charge. But as you've probably noticed, the wires in our house don't start flying wildly around when we plug them into things, so these electric fields must be pretty weak. And indeed, they are. For example, if I were to take two 8mm diameter and half-meter long wires, place them 5 centimeters apart from each other, and then charge them both to negative 5 volts, we would expect somewhere around 200 million electrons to flow into each wire. The excess electrons in these wires would then push against each other, but with a force of only 5 times 10 to the negative 10 newtons, which is 10,000 times less than the weight of a human hair. You would have to go to some crazy extremes if you wanted to see the electrostatic force from your wires, such as this gentleman who charged his wires up to 10,000 volts and was then just barely able to deflect a piece of aluminum foil. At this point, we are very close to being able to explain the physics behind basic circuits. But before we do, there is one final question to answer. If voltage is the result of excess electrons, and if voltage moves along a wire close to the speed of light, does that mean that the electrons from the battery are also moving close to the speed of light? To answer that, let's perform another experiment with some magnets. Here we have 8 magnets representing 8 electrons inside of a copper wire. Sitting next to them are 8 protons, giving the wire an overall neutral charge. I then push an extra electron into the wire, making the wire electrically negative. Notice, however, that when I add the extra electron, the other electrons rearrange themselves so as to maintain a constant spacing. Therefore, while I only moved the first electron an inch or so, the negative electric field extends uniformly throughout the whole wire, meaning that the speed of the voltage change must be greater than the speed of any individual electron. How much faster? Looking back at the experiment, we see that the voltage pulse relies on 2 phenomena. First, each individual electron needs to physically move to a new location. And in a typical circuit, electrons will move through a wire with a speed of around 1 millimeter per hour. Once an electron moves to its new location, the local electric field will then update to reflect this change, and this update travels at the speed of light. Once this update reaches the next electron in line, that next electron will then begin to move, continuing the voltage pulse. Therefore, the overall pulse speed will lie somewhere between the movement speed of the electrons and the update speed of the local field, with the exact mix of the two speeds depending on the distance that each electron needs to travel. The greater the distance traveled by each electron, the slower the overall pulse speed. Now, we said earlier that we would be pumping almost 1 billion electrons into this wire to get it to negative 5 volts. With that many electrons being added, you would think that they would have to travel pretty far along the wire before they became evenly spaced. However, before we even add the electrons to the wire, there are already 10 to the 24 valence electrons inside the wire, sitting next to an equal number of protons. That's 1,000 trillion valence electrons for every new electron from the battery. So, when the electrons do flow in from the battery, they only need to move a negligibly small distance to achieve a uniform spacing. This is also true for the wire attached to the positive terminal of the battery, where so few electrons are pulled out of the wire that the remaining electrons also barely need to move. And since each electron travels such a small distance, the main bottleneck is actually the time spent waiting for the local field to update between each electron, meaning that the voltage pulse will travel down the wire at somewhere between 60 to 99% of the speed of light, depending on the type of wire that is used. Therefore, when I connect a wire to a battery, the movement of electrons will actually look like this. And with that last explanation out of the way, we now know enough physics to explain the workings of a basic circuit. When we connect a pair of wires to this battery, the battery pulls electrons from the top wire and pushes them to the bottom wire, giving the top wire an electric potential of 5 volts and the bottom wire a potential of negative 5 volts. The resulting electric field exerts a force on any nearby negatively charged object, pushing it away from the bottom wire and towards the top wire. If an electron were to escape from the bottom wire, it would also feel these forces, and would therefore accelerate to the top wire, gaining 10 electron volts of kinetic energy along its journey. But since electrons don't normally go jumping off of wires, we connect the two sides with a resistor. The resistor gives the electron a path to the top wire, but it also steals the 10 electron volts of kinetic energy that the electron would have gained, releasing it instead as heat. If we were to pass 1 amp of electricity through the system, which is equal to 10 to the 19 electrons per second, and if each electron gives off 10 to the negative 18 joules of energy as it moves from low to high voltage, then we would expect the resistor to give off 10 joules per second, or 10 watts, of heat. For those of you wondering, this is where we get that power equals voltage times current. Voltage is the energy taken from each electron by the resistor, and current is the number of electrons that go through the resistor every second. And that's how circuits work. For the rest of the video, I will be referring to this explanation of electric circuits, the one based on the idea of electric charges moving between areas of different voltages, as the traditional theory of electricity. And now that you have a good grasp on the traditional theory, you may find yourself thinking that this model strongly resembles a hydraulic circuit. After all, both circuits have some kind of pump that pushes a fluid to a region of high pressure, a high pressure line that transports the fluid, a device where the high pressure fluid can do work, and a low pressure line that allows the fluid to return to the pump. And indeed, it is because of these similarities that the hydraulic analogy is usually used to teach students about electricity. Which raises the question, if the hydraulic analogy is an effective metaphor, why did Derek instead decide to use an explanation involving Poynting vectors? From what I can tell, there were 3 points about electricity that Derek was trying to make with his lesson on Poynting vectors. The first point was that electrons in a circuit don't move very fast. As we've already learned, electrons in a circuit like this will only move at a rate of about 1 millimeter per hour. This means that when this circuit is turned on, electron A will enter the wire from the battery, but electron B will be the one going into the resistor and generating heat. This leads to Derek's second point, which is meant to refute a common misconception about electricity. As Derek himself states,
"These are the lies you were taught about electricity, that electrons themselves have potential energy."
To expand on this misconception, people think of electrons as tiny batteries, which are pumped full of energy at one end of the circuit and are then transported to a resistor where their energy is released. But as we have already learned, particles don't store energy, electric fields do. So, when a battery pumps an electron from the positive wire into the negative wire, it strengthens the electric field around both wires, increasing the potential energy stored in the two fields. And when a different electron leaves the negative wire, it removes potential energy from the electric fields and converts it into thermal energy inside the resistor. So, to the extent that it makes sense to discuss energy flowing from the battery to the resistor, we can conclude that the energy is flowing through the electric fields, since, after all, that is where the energy is being stored. The electrons are only used to add or remove energy from the fields. If you want, you can think of it like a bank. Let's say you deposit a $100 bill in a Los Angeles bank. A short time later, you fly to New York City and withdraw a $100 bill from a bank there. The bank didn't ship that $100 bill from LA to NYC. Instead, when you deposited cash in the LA bank, it increased your digital wealth inside their computer. Then later, the New York bank tapped into that digital wealth before giving you a different $100 bill. The only purpose of the paper money is to provide a way for you to add or remove wealth from the bank's computer, just like how electrons add or remove energy from electric fields. And in the same way that the bank's computer transfers wealth between the different branches of the bank, the electric field transports energy to different branches of the circuit. Lastly, Derek used the Poynting vector description as a way to explain alternating current. Now, alternating current is pretty simple. When a system uses AC, It just means that the direction of the current flips back and forth around 50 to 60 times a second. Of course, if you slept through a lot of your 7 a.m. college physics lectures, then there are ways alternating current could seem counterintuitive. For example, when the system starts out, electrons flow from the bottom wire to the top wire, releasing thermal energy along the way. But when the current flips a few seconds later, the same electrons then come back through the resistor. Does this mean that they extract the same thermal energy that they had just deposited? And if electrons just wiggle back and forth, then how does energy travel from the battery to the resistor? The key to AC is that the voltage direction flips at the same time as the current direction. Therefore, no matter the current direction, electrons are always escaping an area of high electron density for an area of low electron density, meaning that electrons are releasing thermal energy into the resistor during both halves of the cycle. Basically, if this picture makes sense to you and this picture makes sense to you, then you know enough to understand AC power systems. So there you go. Derek's three main points were A, that electrons move slowly through a circuit, B, that energy is transported in the field around the wire instead of through the electrons in the wire, and C, that alternating current doesn't rely on black magic. And as we have seen, with a proper understanding of electric circuits, those 3 points are pretty easy to understand. Now at this point, I bet a lot of you are thinking, so if the traditional explanation can adequately describe circuits, as well as explaining Derek's 3 main points, then how does the Poynting vector fit into this? Are the 2 explanations at odds with each other, or are they compatible? And to answer that question, let's see how Poynting derived his vectors in the first place. The derivation behind the Poynting vector is rather complex, but it uses as its starting point 3 equations. The first equation is Faraday's law of induction, but in the circuits that we will be looking at, meaning circuits without any inductors or transformers, the change in the magnetic field should be negligible, meaning we can ignore Faraday's law. The other 2 equations are Ampere's circuit law and the work-energy law for charged particles. This last equation states that the rate of work done on a collection of particles is given by the dot product of the electric field and the current density. And if you wave away all the fancy vector calculus notation, you end up with power equals voltage times current, which was the equation we just derived in the process of explaining circuits with the traditional model. And since Poynting used as his starting point our fundamental equation from earlier, we see that the traditional model and the Poynting vector aren't rival explanations. Instead, the Poynting vector is the direct descendant of the traditional model. Therefore, if you use the Poynting vector to analyze energy flow through a circuit, all you're doing is repackaging the power equation in a way that hides the current term. Let's see how it does that. Returning to our example circuit, we know that energy is flowing from the battery on the left to the resistor on the right. We also know that the battery pumps electrons from the positive wire to the negative wire, and that the resistor allows them to flow back in the other direction. Therefore, the electrons must everywhere be flowing in a counterclockwise direction. This leads us to notice that on the negative wire, the energy flow matches the electron flow, whereas on the positive wire, energy flows in the opposite direction as the electrons. And this is true no matter how we orient the circuit. So, we conclude that if you want to use traditional circuit theory to determine the energy flow around a conductor, you need to know the voltage of the wire and the electron flow direction. Now let's see how you determine energy flow using Poynting vectors. The first step is to draw in the electric field lines. As stated earlier, electric field lines point away from areas of positive charge and towards areas of negative charge, so that part is easy. To draw in the magnetic field lines, we need Ampere's law, which states that a magnetic field will form around any current-carrying wire in the direction given by the rotational right-hand rule. Of course, thanks to Ben Franklin, we are stuck with an electric current defined as opposite the direction of the flow of electrons. Normally this is no big deal, but since this video has been using electron flow thus far, I decided to continue the practice with Ampere's law. Therefore, instead of pointing the thumb of your right hand in the direction of positive current, we shall instead point the thumb of our left hand in the direction of electron flow. Or, if that hurts your brain, then continue using the right hand rule and just make sure that you convert from electron flow to conventional current flow for these next examples. So with our left hand rule, we can draw in the magnetic field lines as well. Lastly, we use the cross-product right-hand rule to determine the direction of the Poynting vector. And with the Poynting vectors added, we notice something interesting. On the negative branch of the circuit, the Poynting vector points in the same direction as the flow of electrons, regardless of how we orient the wire. And on the positive branch, the Poynting vector points in the direction opposite to the flow of electrons. So we find that, even though the Poynting vector analysis uses a different set of inputs, it returns the same answer as the traditional analysis about the connection between the flow of electrons and energy flow direction. Of course, this makes sense when you realize that wire voltage and electric field direction are basically synonyms, and that the magnetic field is determined by the electron flow. So what appears to be two different methods to analyze the circuit turns out to be the same method, with the magnetic field direction serving as a proxy for the electron flow. We can perform a similar analysis on the battery and resistor. These components serve as junctions between different voltages, meaning that the electric field lines near these components are parallel to the wire. As we learned earlier, power sources add energy to electric fields by pumping electrons from areas of positive voltage to areas of negative voltage, whereas power sinks remove energy from fields by allowing electrons to flow from negative voltage to positive voltage. But in addition to determining if a component adds or removes energy from a circuit, these different electron flows also determine the direction of the magnetic field around each component. So, using our right-hand rule, we find that components which add energy to a circuit have a Poynting vector that points outwards, while components that remove energy from a circuit have a Poynting vector that points inwards. So again, it may initially appear as if the traditional and Poynting methods are distinct approaches for analyzing circuits, but because voltage and electric field directions are synonyms, and because electron movement determines magnetic field direction, the two approaches end up being quite similar and return the same results. So, if these two methods are really the same method, is one better suited for introducing students to the idea of electricity? Because in his video, it did seem like Derek was pushing for the Poynting-based explanation to be taught as the introductory model. And it was that inference that I found to be the most strange, because there are several problems associated with learning the Poynting-based explanation first. First of all, as we've already seen, the derivation of the Poynting vector starts with the fact that power equals voltage times current, along with Ampere's law. So, if you wanted to understand why the Poynting vector works, you'd have to first learn those two equations, along with about a semester's worth of vector calculus. And if you are going to learn about P equals VI, then you'll probably end up learning the standard explanation in the process. So instead of trying to rush into a discussion of Poynting vectors, why not just take the time to make sure students thoroughly learn the standard model? There are other problems associated with switching to a Poynting vector-based teaching approach. For example, let's say you found a copper box, drilled some holes in it, and then took the light bulb circuit and placed half of it in the box. Would the circuit still work? Now, someone taught with the traditional explanation of circuits would guess that, yeah, the circuit would still function fine. After all, there is still a voltage difference between the two wires, and current is still flowing through the circuit, so power should still be delivered to the bulb. But that answer may not be as obvious to someone taught with the Poynting explanation. After all, electric fields don't exist inside conductors, and since the Poynting vector is proportional to the strength of the electric field, it would be reasonable to assume that the Poynting vector would also be blocked by the box, meaning the light should turn off. Of course, our cars are filled with wires running through holes in conductive sheet metal, and yet my lights still turn on just fine. Therefore, this box probably won't block energy flow either. To see why, let's look at a cross-section view of the circuit without the box. As we can see, an electric field fills the space between the positive and negative wires. And since the Poynting vector is proportional to the electric field, it must also fill this space. But now let's run the wires through the holes in the copper box. When the wires are first placed in the box, the electric field passes through the copper. The electric field interacts with the electrons in the copper, pushing them from the negative wire to the positive wire. The movement of these electrons creates a charge distribution along the walls of the two holes, and this distribution blocks the electric field lines from the wires, meaning that the electric field strength in the bulk of the copper becomes zero. However, The presence of charged particles so close to the wires also results in a much stronger electric field in the gap between the wires and the box. So while the Poynting vectors are confined to only the region between the wires and the box, the stronger electric field leads to a much more intense Poynting vector that compensates for the smaller area, meaning the same amount of energy is transferred by the Poynting vector. You could completely eliminate the gap between the edge of the hole and the insulation on the wires, but the electric field would only become all that much stronger, leading to the same amount of energy transfer. So instead of blocking the Poynting vector, the copper box actually redirects it, with the same amount of energy being delivered in both cases. This may lead you to ask, what if we made the holes even smaller by removing the insulation from the wires? Well, in that case, since copper is a conductor, electrons would be free to move directly between the two wires, bypassing the light bulb. Without any substantial resistance in series with the battery, the circuit would transform itself into a DIY hand warmer, and if you were lucky, the wires, and/or the battery, just might catch fire. But power would be prevented from reaching the light bulb, so mission accomplished, I guess. Anyway, the more problematic misconception that can come from only learning the Poynting vector explanation was actually illustrated by Derek himself with his thought experiment. As a reminder, Derek opened his video by showing a hypothetical circuit that was 300 million meters long and 1 meter wide. He then asked, if the switch were closed, how long would it take before the light bulb turned on? As we can see, 1 light second's worth of wire separates the switch from the light bulb. And we have already learned that voltage updates travel down the wire at close to the speed of light. Therefore, 1 second seems like a reasonable answer for the time delay between flipping the switch and the light turning on. However, according to Derek, this answer ignores the nature of the Poynting vector. Since the Poynting vector shows the flow of energy, and since the vector directly spans the 1 meter distance between the two halves of the circuit, we should instead use 1 meter as the distance that the signal needs to travel. Therefore, the delay between closing the switch and the light turning on should only be around 3 nanoseconds. Unfortunately, this explanation leaves out 2 crucial details. The first, and admittedly more minor detail, relates to the way that the vectors are drawn. Thus far through the video, we have drawn our circuits with the Poynting vectors spaced evenly through the diagram. However, it turns out the electric field is not equally strong throughout the whole circuit, but is instead strongest near the wires and is weaker away from them. Likewise, if we look at a cross-section of the wires, we will see that the magnetic field is also strongest near the wires. And because the Poynting vector is proportional to the electric field times the magnetic field, the Poynting vector is not evenly spaced throughout the circuit, but is instead also strongest near the wires, meaning that the energy transfer is heavily localized to that region. Therefore, for the thought experiment circuit, instead of the energy flow looking like this, it will actually look like this, or, if my back-of-the-envelope math is to be trusted, possibly even like this. And because the 1 meter long Poynting vectors in the middle of the circuit represent such a small portion of the overall energy transfer, we would expect that very little energy would reach the light bulb in the first second. But as it turns out, this question about the final pattern of energy distribution is actually a red herring. By getting into the details of the relative strength of the Poynting vector close to versus far away from the wires, I am implying that this is how the Poynting vectors will look once the switch is flipped. However, even though this is what the Poynting vectors will eventually look like, that does not mean that they will look like this right when the switch is first flipped. To figure out the transient Poynting vector field, we need to investigate what happens in the wires during that crucial first second. Before the switch is closed, we see that most of the circuit is connected to the positive side of the battery, and so most of the circuit will be positively charged, with only the wire between the negative side of the battery and the switch being negatively charged. Then, at time equals 0, the switch is closed. At that moment, there is a junction where the negatively charged wire meets the positively charged wire. And since electrons are attracted to regions of positive charge, they will begin to flow across the junction from right to left. But as we have already learned, when there is a junction where electrons flow from negative to positive, then the Poynting vector will point towards that junction. Therefore, the Poynting vectors will be pointing at the wavefront, not at the light bulb. As the wavefront moves along the wire, the Poynting vector will follow. Actually, there are two wavefronts emanating from the switch, one moving to the right that we can see, and another moving towards the left. Once one of these waves reaches a section of wire, electrons will start to flow, creating magnetic fields. So, when the left wavefront passes through the battery, Poynting vectors will develop on the left side of the battery as well. These two waves travel down the wire at the speed of light, changing the shape of the Poynting vectors as they move. 1 second after the switch was flipped, the two wavefronts finally meet at the light bulb. It is only at this moment that the Poynting vector points at the light, indicating that electrons are moving across the filament and depositing energy, causing the light to turn on. The big lesson here is that the Poynting vector at the light bulb is proportional to the electric and magnetic fields at the light bulb. If there is not a voltage difference across the light, or if there is no current moving through the filament to create the magnetic field, then the Poynting vector will be zero at the bulb. And if it takes a full second for the voltage and current to travel from the switch to the light, then it will also take a full second for the Poynting vector to point at the light bulb. So, there you have it. Despite what the Poynting vector may show, the correct answer to Derek's question is B. It will take 1 second for the light to turn on after the switch is flipped. Is what you would hear me say if Derek was actually wrong here. But come on, this is Veritasium we're talking about, not the History Channel. Nothing that Derek says is ever going to be 100% wrong. And indeed, there is one final piece to the puzzle. Do you remember a second ago when I said, and if it takes a full second for the voltage and current to travel from the switch to the light, then it will also take a full second for the Poynting vector to point at the light bulb. I mean, I hope you remember that. I literally just said it. Anyway, the Poynting vector will not develop at the light bulb until current and a voltage difference appear across the light bulb filament. But what if it takes less than 1 second for those two things to appear? Here we are back at the circuit. As we said earlier, when the switch is closed, the electric field around the bottom wire will start changing. But as we have already learned, electric fields exist outside of wires, so let's draw the fields in and zoom in on one section of the circuit. Initially, the electrons in the top wire feel a slight attractive force to the positive electric field on the bottom wire. But as the wavefront moves across the bottom wire, that attractive positive field turns into a repulsive negative field, pushing the electrons away. Some electrons are pushed to the left, increasing the electron density in this portion of wire, decreasing the voltage. This results in a voltage difference across the light bulb, encouraging electrons to flow through the light and deposit energy. And since energy is being transferred from the bottom wire to the top wire, there will be a corresponding Poynting vector connecting the two wires, in addition to the set of Poynting vectors that we found earlier. This transmission of energy through parallel wires is known as capacitive coupling, and is sometimes used for wireless charging. How much power is delivered to the light bulb by this capacitive coupling? Some insight can be gained from the channel Alpha Phoenix, who ran a small-scale experiment with about 1 kilometer of wire. His basic setup is shown in this diagram, with the important takeaways being that A, the white probe gives the voltage across his light bulb, and B, that he has about 1.6 micro light seconds of wire between his switch and the bulb. Here is the output from his experiment, and covering up some unimportant signals, we can see that the current across his resistor rises to 0.2 milliamps right when the switch is first flipped. And then 1.6 microseconds later, after the wavefront has had time to travel through 500 meters of wire, we see that the current rises again to 1.7 milliamps. So the transient current appears to be around 14% of the final current. And since power is proportional to the square of current, we find that the transient power delivery is about 1.5% of the final power, which isn't a lot of power, but Derek's criteria for the light being on was
the light bulb has to turn on immediately when current passes through it.
And with that definition, then D is the correct answer to his question, in a purely technical sense anyway. But in all seriousness, it wasn't the answer to Derek's question that drove me to make this video. It was his explanation. Derek took this picture of the Poynting vectors for the circuit, pointed at the vectors in the middle, and claimed that they were responsible for the short 3 nanosecond delay. But these Poynting vectors are not the same vectors that deliver power during the transient period, and we can tell that by looking at them. These vectors are strongest near the battery in a light bulb and get weaker towards the ends of the circuit. But during the transient period, the Poynting vector associated with capacitive coupling does not weaken as it moves along the circuit. So even though we have two sets of Poynting vectors that both appear in the middle of the circuit, they are actually different vectors. And they are different because they are the result of different electric fields under different conditions, and they represent different kinds of energy transfer. This can be further demonstrated by looking at a situation where conduction is impossible. For example, let's take our circuit and cut the wires at each end. Now, it may appear that no energy can reach the light bulb from the battery, but if we were to flip the switch, we would observe the same capacitive coupling effect, meaning the light bulb would receive the same amount of power for the first second. In fact, Alpha Phoenix ran this test with his small setup and saw the same 0.2 milliamp jump for the first 1.6 microseconds. So even though there is no steady-state Poynting vector for this setup, we still see the Poynting vector during the transient period, showing that one does not necessarily correlate with the other. And as a final thought, I should point out that it is also possible to block capacitive coupling without impeding conduction. We've already seen that a copper box will not interfere with conduction, but because metal blocks electric fields, such a box would prevent the changing electric field on the bottom wire from affecting the top wire, meaning that the light bulb would remain completely off until the wavefront reached it. If Alpha Phoenix had run a similar test, his results probably would have looked like this. Anyway, I don't have anything against Poynting vectors. I'm not some kind of traditional explanation zealot, if you will. If I actually knew any electrical engineering, I'm sure I would be aware of all the wonderful ways that Poynting vectors make design work so much easier. But when it comes to teaching the theory of electricity, it's my opinion anyway, that Poynting vectors are not the right tool for the job. And now, you know why. Thanks for listening. There is one last thing that I should mention. Throughout the video, I discuss electric fields as existing outside of wires. But do electric fields also exist inside of wires? To explore that question, let's add some excess electrons to this wire. These electrons push on one another, forcing them all to move to the perimeter of the wire. When we add a test particle to the inside of the wire, we see that it is equally pushed on in every direction. So, just like how the electric field strength between two positive particles is zero, the electric field inside any conductor is also zero, even though it might be quite strong outside of the conductor. This is also true for wires that carry positive charge. If we remove some electrons from the middle of the wire, other electrons are pulled in from the edge, leaving the holes all on the outside. Therefore, the positive electric field also only exists outside of the wire. Of course, by getting into this discussion, I invite viewers to ask, so excess charge only exists on the outside of the wire? Is this related to the skin effect that I've heard so much about? The skin effect says that for high-frequency AC systems, most current travels in the outer layer of a wire. However, this is a different phenomena and is driven by complex interactions with magnetic fields. For simple DC systems, even though excess charge exists only on the outside of the wire, electrons still flow through the whole cross-section. Let's see how this works. Here we have a length of wire with a net electric charge on the wire's surface. Now let's say that these surface electrons start flowing from left to right. This causes the number of electrons on the wire's surface to decrease in the direction of electron flow. This decrease in the surface electron density then creates a weak electric field inside of and along the axis of the wire, encouraging paired electrons to flow throughout the whole cross-section of the wire. The decrease in the concentration of electrons is proportional to the resistance of the wire. The less resistive the wire, the smaller the decrease in electron surface density, leading to a weaker internal electric field. On the other hand, we see that the electron concentration changes very rapidly as electrons pass through a resistor, represented here by a narrow strip of wire. This rapid change in electron density creates a very strong electric field inside the resistor, which helps push electrons through, giving off heat in the process. So, In areas where the electric field exists mainly outside the wire, energy is mainly being transported. And in areas where the electric field exists mainly inside the wire, energy is consumed and is given off as heat. If we were to draw in the electric fields for our main diagram, it would look something like this.